In this session, we are going to discuss a question from CSIR NET December 2024. We are given two non-interacting identical spin-off particles. They are placed in a 2D infinite square well of side L. Their wave function, spatial wave function is 2 by L sin nx pi x by L sin ny pi y by L. Now the total spin state of the particles is j equal to 1, m equal to 0. We have to find the lowest possible energy eigenvalue. Now the particles that we are given here is identical spin half particles, and we know that spin half or spin 3 by 2, spin 5 by 2, all of these particles are fermions. Fermions are particles with half odd integer spin. Therefore in this problem we have identical fermions, and for identical fermions recall that total wave function for identical fermions, this must be antisymmetric. Why do we say this? Because then only Pauli exclusion principle will be satisfied. To satisfy Pauli exclusion principle. Now total wave function, this is the product of spatial wave function times spin wave function. In the question they have used this letter for this symbol for spatial wave function, so let us use that itself. Phi nx ny, this is spatial wave function times spin wave function, so their product, it must be antisymmetric. This must be antisymmetric. Now we are given the total spin state to be equal to j equal to 1, m equal to 0. Now j equal to 1, m equal to 0, this is triplet state, and triplet state is symmetric. Therefore the given spin state, this is symmetric. And for the total wave function to be antisymmetric, we need this wave function, the spatial wave function, this must be antisymmetric. I don't know if you are new to this triplet state. I will give you a brief introduction. So for two spin half particles, they can have triplet state or singlet state. They can have three types of triplet states, which are j equal to 1, m equal to 1, or they can have j equal to 1, m equal to 0 state, j equal to 1, m equal to -1. So in this case you have a state like this, both are up. In this case you have both the spin states are down, both are spin down. In this case you have something like this, 1 by root 2 spin up, spin down, plus spin down, spin up. Now all of these spin states, they are symmetric. Why do we say that they are symmetric? If you exchange any particles, any two particles here, let's label this as 1 and let's label this as 2. Now if you exchange 2 and 1, then what happens? You will get the same thing back. That's why we are saying these are symmetric under particle exchange. If you do the same thing for this also, you will get the same thing back. If you exchange particles in this also, you will get the same thing back. That's why we are saying triplet states are symmetric. Now there is antisymmetric state for spin 1 by 2 particles, two spin 1 by 2 particles, which is singlet state. Here you have j equal to 0, m equal to 0. In this case you have a state like this, 1 by root 2, up, down, minus, down, up. Now if you exchange the particles, then under swapping So after swapping you will get the new wave function 1 by root 2 Now look at this. We are getting the same thing back but with a negative sign, right? So that's why we are saying this state is anti-symmetric. Now let us come back to the problem. We have to get the total wave function anti-symmetric, then only Pauli exclusion principle will be satisfied, and the given spin state is j equal to 1 m equal to 0 state, which is triplet state, and triplet state is symmetric. Therefore the spatial wave function must be anti-symmetric. Now the spatial wave function phi nx ny, this must be anti-symmetric. Wait a minute, we used phi nx ny for total wave function, but it is not. It is this phi nx ny, it is single particle spatial wave function, but we need the total spatial wave function. This must be anti-symmetric. So we cannot use phi nx ny for total spatial wave function. So here also you can edit. This is total spatial wave function, psi spatial, and phi nx ny given in the question, it is single particle spatial wave function. This psi spatial, this is two particle wave function. Alright, so total wave function, total spatial wave function, this must be anti-symmetric. Now if we place both the electrons in the state nx ny equal to 1 1, then we will get psi spatial. This will be of the form phi 1 1 x1 y1 phi 1 1 x2 y2, which is symmetric. This is symmetric then, and it will violates Pauli exclusion principle. Therefore we cannot put both the electrons in nx and y equal to 1 1 state, because then the spatial wave function that is created, it will be symmetric, and then it violates Pauli exclusion principle. So what we can do is we can place one electron in nx and y equal to 1 1 state. So it is not electron, it is not specified it is electron, it is spin half particle. It can be electron or any other particle. So you can place one particle in 1 1 state, and the second particle you can place it in 1 2 state, or you can place it in 2 1 state, because both are degenerate states. In this case the two particle spatial wave function will be equal to something like this: 1 by root 2 phi 1 1 x1 y1 phi 1 2 x2 y2 minus phi 1 2 x1 y1 phi 1 1 x2 y2. So this state is antisymmetric now. And what will be the energy of this state? So energy of the state phi nx ny is E is equal to pi square h bar square divided by 2m L square. L is the length of side of the potential well, 2D potential well, times nx square plus ny square. So the energy of phi nx ny state is E nx ny. Now there is one particle in phi 1 1 state, therefore 1 times E11, and there is one particle in phi 1 2 state, so 1 times E12. This is equal to 1 times pi square h bar square divided by 2m L square times 1 square plus 1 square plus E12 is pi square h bar square divided by 2ml square times 1 square plus ny square is 2 square, which is equal to 7 pi square h bar square divided by 2ml square. Therefore the correct option here is option 4.